Thank you for inviting me. My name is Jeroen. I was born in Holland, in Amsterdam, but after many travels, I live now for 30 years in Brazil. Um, well, maybe less, but so I am in cryptography like for 40 years or so. I was actually sort of present in all the beginning of cryptography. You know, before it was only to the military and things like that. And then when by the end of the 70s, 80s, then things it started to become a research topic, like when RSA started. Anyway, I won't talk too much about the history. I'm gonna give. I understand the talk is going to be an hour more or less. I'm going to give an introduction to cryptography and also talk a little bit about zero knowledge. This is a huge topic, and I also noticed there are other classes dedicated to cryptography. So I made a selection which I thought was appropriate. So the topics for today are those. What is cryptography? I'm going to give like a definition of cryptography and give an overview of it, including two important examples. Maybe you know them, but maybe you don't realize how important they are. Then I'm also going to talk using these examples, explaining some of the notions of what security actually means in cryptography. And then I will give a first introduction about zero knowledge and snarks, and then 2 weeks from now, I will have a deeper, more time to have one full hour to talk about zero knowledge and snarks. But I think it's already good to make a small start, so you know what this is about. So the first thing is I'm sort of giving a definition of cryptography, and I'm giving my own definition first. So the definition is cryptography is a sub-area of information security that deals with mathematical methods to accomplish secure communication and also joint computations in the presence of malicious parties. So there are some important aspects here in this definition. In most settings, the legitimate parties are geographically separated, and often they communicate over an insecure channel. This is, I'll show next, but this
You are on mute, Jeroen.
I didn't hear what was being said. I think it was about integrity.
No, I think somebody just got unmuted their microphone.
Oh, okay. And in some setting, the separation is not geographical, the separation is in time. So an example is that you can encrypt data, store it in a database, and then you store it in an encrypted way, and that data you can retrieve it. So this is my definition. I have other definitions here. A lot of this talk is based on the Handbook of Applied Cryptography, which you can find online. I can provide reference for that. I get distracted when people talk, so either you have a question or please make sure your microphone is closed. So cryptography is a sub-area of information security that deals with mathematical security properties such as confidentiality, authenticity, integrity, and non-repudiation. So what I don't like about the definition is that it's not as complete as I would like to. You can also put cryptography in the context of distributed systems. So a distributed algorithm is an algorithm that is run by several different parties who trust each other to accomplish some goal. And then you can define cryptographic protocols as distributed algorithms in which parties do not trust each other. It's very important that you understand that cryptography, essentially, there's always a sort of a distrust. Our parties don't really trust each other for various reasons. Because if everybody trusted each other, then there would be no need for cryptography. Well, I'm going to make this point repeatedly. Make always sure that you visualize and understand the setting, and there's also part of protocols. An important part are local computations, but the essence is the exchange of messages. So here I show a very basic protocol that everybody already knows. It's like Alice and Bob, they live on different places on the planet. Maybe one lives in, I don't know, in Tokyo, and the other one lives in Singapore, and they would like to communicate to each other. They use the internet, but the internet is insecure, so there might be an adversary who is trying to eavesdrop and intercept a message. So this is the basic protocol. I have here the same. This is the same idea. So we have Alice, we have Bob. What they do is they usually, you can imagine, they have an encryption algorithm. You get the message M, you get the secret key K. They apply encryption. The adversary gets to see the encrypted message, the cryptogram, sometimes it's called. The Bob, who receives the message, has the same key as Alice, so he can decrypt the algorithm to get M prime, but of course we want that, suppose that M prime and M are the same. So this is one of the basic scenarios. I call it the mother of all protocols. It's as old, at least, as Julius Caesar, maybe older than that. There are various old-fashioned solutions and very modern solutions. Like today, we all use the advanced encryption standard. And we suppose that Alice and Bob use the same key K. And this is something we have to address. How do Alice and Bob agree on the key K? And here you can see the same diagram. What we suppose is that there is a secure channel in which on which the secret key K is transported from Alice to Bob. Okay, so, and there are various ways you can imagine a secure channel. The easiest way to have a secure channel is if Alice and Bob have met each other and then they share a secret key. I don't know, Alice has a key, she makes a copy, maybe a photograph or a Xerox, and gives it to Bob, and then they share a key. But in many, so in diplomatic, I'm absolutely sure that in diplomatic message transfer, they still use this. It's the best, the most secure way. So what we see sort of is that the problem of secure communication, you can split it into the problem of secure key distribution and secure message encryption. Okay, later on, I will be explaining this into more detail. later today. I just want to discuss a little bit more in a general context. So I believe that the central concept of cryptography is a cryptographic protocols. So I already said what it is. Messages are sent between parties following prearranged rules. There are local computations performed by parties, and they want to reach some common goal. And again, the protocol should be resistant to some parties not following the rules. So they may behave in a dishonest way. In some protocols, the local computations are the dominant part. And so then we talk about cryptographic algorithms. In particular, a huge part of cryptography is dedicated to encryption and decryption algorithms, digital signatures, the algorithm to sign, and the algorithm for verification, and hash functions. Yeah, as I say here, these primitives, they sort of constitute the bread and butter of cryptography. I will go a little bit beyond that. I sort of assume that most of you already have an idea of the encryption algorithm, message signatures, and hashing. And by the way, they will be discussed in some other lecture. So I'm trying to focus on a slightly different topic. From a higher level, we should realize that cryptography is a sub-area of information security, and information security encompasses many things. It encompasses physical security, computer security, network security, cryptography, as I said, the mathematical aspects of information security. It is about making sure that your business is always online. If there is an incident, that you don't stay out of business for several weeks, because then your company may go bankrupt. There are political, juridical aspects, economical aspects, and even psychological, personal aspects. We will see this later on. But it's like about hiring persons and making sure that people will not leak information. These are aspects of information security as a whole. Let me say that cryptography pervades every day. This is sort of surprising for me. When I started researching cryptography, this is like in around 80, 81, 82, we didn't have, I would not have expected that cryptography would be such an important thing for everyday life. It started with the internet, in which you want to protect communication over an insecure channel. Then we had all the wireless revolution. So we do have that Wi-Fi, for instance. We all know that you need a password. So cryptography is really increasing. I put here some more modern demands. It's like how to benefit securely from new information technology. It's like worldwide connectivity, free data storage, free processing, how to mitigate erosion of privacy, which is also a very important issue nowadays. Yeah, this is so this is what I mentioned. But you can read this, but how can I say? How to sign a contract on the internet, how to do an auction on the internet, so let's take the one but last example. How do you protect your fridge? I mean, if we are going to have the Internet of Things, then maybe my fridge will go connected on the internet. But if I take like 5 beers on Friday night and my student can hack my fridge, then my students will know how many beers I had been drinking the night before. So there's clearly a privacy issue there. And of course, the new challenge that I'm not mentioning in this particular slide is the blockchain. This is why we're all here. We're talking about blockchain and in particular about zero knowledge. Here I put a very basic example of a protocol just for you to think about. So imagine that we have 4 banks. They want to compute the sum of their losses with internet fraud. So bank 1 has lost X1, bank 2, X2, etc., etc. So they want to compute the sum of their losses, but each bank would like to maintain its own loss private. And actually, it's better, I have it, all the steps, I have it here, but it's better to look at this slide. The word bank here is in Portuguese, but that shouldn't be a problem. So what each bank does is it creates a random number for each neighbor. Okay, so so bank 1 chooses a random number to talk to bank 2, bank 3, and bank 4. Okay. So this is what you see here. Bank 1, it has a random number R12 with it shares with bank 2, R13 with it shares with bank 3, R14 with it shares with bank 4. So everybody does it. So everybody sends out 3 random numbers and everybody receives 3 random numbers. And now what they are going to do is the following. So the X is their actually lost. So the X here, X1 is the input of bank 1. And it's going to add all the random number that it sent, but it's going to subtract all the random numbers that it's received. And this is the value Y1. But there is an important aspect here that I sort of glossed over. Because before everything starts, the banks, they will need to choose a very large number, like it's never going to be more than $100 billion, and they use that as an upper bound. And so all the computation, the choices of the random numbers and all the computations, so the random numbers are chosen between 1 and, what did I say, 100 billion. And also the randomness will be all in this interval. And the computation here will be done modulo that random number B. So they all do this. So bank 1 does that, bank 2 does the same, bank 3 does the same, and bank 4 does the same. And each of them publishes the Y. So bank 1 publishes Y1, bank 2 Y2, bank 3 Y3, bank 4 Y4. And so each of them, they can compute the sum. Again, modulo this large number B. And now what happens is very basic. If you think about it, each random number that is added will be subtracted by some other bank. So if you look, for instance, at R12, okay, R12 is received by bank 2 and will be subtracted by bank 2. So the number here, R12, that's added by bank 1 will be subtracted by bank 2. So what happens is when you compute this sum is that all the randomness will cancel, and the only thing that will remain will be the sum of X1, X2, X3, and X4. So this is an example of cryptographic protocol, a very basic example, but nevertheless, I find it cute to introduce the idea of cryptographic protocols. Because so these topics are it's like the confidential, I think these are the main goals of cryptography. It's about confidentiality. So it's like privacy, that nobody can see what you're communicating. It's like authentication. So you know for sure that you are talking to the right person and that the message has not been changed. This is also related to integrity. So that messages are not modified. Non-repudiation is closely related to digital signatures. It's like
Sister was not audible.
Hello.
I don't know what to do. Should I go on?
Yeah,
I don't know if
please go
people
on, guys.
are.
We're taking questions at the end. If you have anything, just raise your hand.
Can I ask in between?
Go ahead.
Sorry.
No,
sorry.
let's keep it at the end, please.
So non-repudiation makes sure that you cannot deny you do something, and you cannot later say that you didn't do it. So this is what digital signatures typically provide. Availability is often mentioned in the context, but I find that availability isn't really something about cryptography. There are no cryptographic protocols that make sure that your service is online. This is something, it's a wider scope. And then we have access control, which I think is pretty obvious, to make sure that the right people have access to the right resources or the right information. Next slide, please. Yeah, and so we have I copied it from the Handbook of Applied Cryptography. And here you can see how various tools contribute to these goals. So for instance, on the left, you can see that for confidentiality, you want encryption. Encryption can be obtained either by using stream ciphers or by block ciphers. So there's also once it's sort of isolated, you worry about efficient implementations, of course, because you want things to be efficient. Let's take another one. Message authentication usually is a combination of, let me see, of hash functions and also of digital signatures. So this is on the right. You can see the hash functions and the digital signatures. They combine. So this is sort of interesting overview, a division of crypto. So please, next slide. So now we get the problem that, yeah, you should scroll on to the last one because they are incremental slides. So no, please go back one. Yeah, this one. So the basic protocols and primitives are key exchange, key management, encryption, decryption, hash functions, and digital signatures, identification techniques, and pseudo-random number generation. These are sort of the basic building blocks. I will give only some basic examples, but otherwise this will be done in some other class. Next slide, please. Here is some terminology that you may find interesting. It's quite a list. I don't want to do it all, also because of the time. For instance, we see here timestamping. Timestamping is very related to the blockchain. So timestamp is like you produce a document and you want to show that the document existed at some moment in time. And one way you could achieve this is you can have a hash of the document, and then you want to sort of make the hash public. Traditionally, this was even done by publishing hashes in newspapers, or you can also make hashes of hashes. Right? You can build a tree of hashes. just like the Merkle tree. And then you can publish the root value in a newspaper. Today, we would use a blockchain to do this. So the blockchain is sort of incorporate this timestamping functionality. Next slide, please. So here we see a big division, an important division. We have primitives that don't have any key, and an important one is the hash functions, which are of arbitrary length. Also, random sequences would produce arbitrary length. We will have primitives that are based on symmetric key and primitives that are based on public key. And I'll be giving an example in a couple of minutes. Next slide. So security is measured in cost, and the cost is something that sometimes that's relative. So the cost of breaking the system must exceed the value of the information protected, or related to that, it can also be related to the time. So say, for instance, that a specific there's some specific authentication mechanism and the response time is 1 second, then if it takes like a week to break the system, then a week may seem, oh, it's not secure. But if the response time is 1 second and you cannot break it in 1 second, then this may still be good enough. So cost is always something that you may want to evaluate. And sometimes, so you need, for instance, also to think about what is the lifetime of the system that you are designing. If you are designing a system whose lifetime is a couple of days, this is completely different from a blockchain whose lifetime may be decades and decades. So this is one consideration. Also, I got disrupted again by somebody who wants to join the call. I'm going to deny it.
Yeah, let's go ahead because we're not admitting it.
Yeah, I get distracted. Yeah, okay.
Yeah, I know.
So the other thing also is that people get this wrong. Digital signatures, you don't. If a signature algorithm is under threat, then what you can do is you can re-sign everything. This is contrary to encryption algorithm. Once you encrypt an algorithm, you cannot redo it. If the algorithm will be broken 50 years from now, then everybody can see what's there. Okay, so this is I only get denies people entering the call. Anyway, I don't know what to do.
Oh, I think you might be getting, because I added you as co-host, just so you could buy. I'll get rid of that so you don't get to look at the admit. All right, let's continue.
Okay, that may.
Yeah.
I get a ding dong and everything. Okay, so cost is important, and related to cost maybe is the next topic. So you must also evaluate who is your enemy. That's the next slide. I put here in a large range of possible enemy. Sometimes you need your security may depend on a careless user who doesn't protect his password correctly. This is on the simple end. On the other end, you can have terrorists, you can have organized crime, or you can have the secret services of some company. So some countries, right? Maybe you want to protect yourself against the I don't know, the Secret Service of Russia or the Secret Service of the United States. So this you need to think about that. Oh, next slide, please. And so also there are various types of attacks. You can have passive attacks. You can have eavesdropping or interception. Traffic analysis is something that's interesting. In the case of traffic analysis, you don't see the contents of the message, but you see who's talking to whom. So this may be important. If you can see, if you have a fleet and you can see who's talking to whom, you may derive from it which ship has the admiral, so which is the main ship if you want to attack it. The man in the middle attack is like it's like this. So chess master A is well, what you do is you have a man in the middle, and he on the one hand he's playing chess with chess master A, and on the other hand he is playing chess with another chess master B. But the only thing the man in the middle does is just relaying the messages, relaying the moves. And so the man in the middle, he seems to be very clever, but nevertheless he isn't contributing anything. So the main lesson of these examples is that in every situation you must specify, you must at least keep in your mind what do you think is the capability of your adversary? What do you think he can do? What is the adversarial model? If you don't do that, then you cannot analyze the security system. So I'll give you an example. A couple of years ago, I was started to study the Internet of Things. And one of the things that always bothered me is that there is very weak definition of what exactly is the capability of the adversary. In the case of the Internet of Things, do you suppose the adversary can intercept a sensor, intercept some item, and reverse engineer it or not? I mean, these are very serious questions. The next slide is about an important notion. It's called the work factor. So this is more of how can I say, a mathematical or a computational notion of security. It says that the work factor expresses the amount of computational effort that's required to break a system. So if you think of a brute force attack, then the work factor is essentially the size of the search space. So if you think of a password that has 12 digits and all the digits are equally likely, then the work factor would be 10 to the power 12. But it's important also that most of the time we like to express the work factor in bits. So if you do I'm going to do a very I can say it off my head computation. So 10 to the 12, it's about 10 to the third to the fourth. And now 10 to the third is about 1024. So it means that 10 to the 12 is about 2 to the 40. So that means 40 bits of security. Okay, so this is how we define the work factor. We usually express it in bits. So if a password is 64 bits, which are equally likely, then the work factor is 2 to the power 64. There's a mistake in the slide. Or just we say it's 64 bits, right? For those who know this, if you look at the definition of the Shannon entropy, then this takes care of the cases that the distribution is not uniform. So there is a definition, an extension of this notion, which is called the Shannon entropy. Next slide, please. And so at this moment, I would say that 90 bits, or so a search space of 2 to the power 90 is considered infeasible. So it's like a minimum level of security. Usually we take 120 bits of security because it's the next power of 2. Most of the time, the implementations are fast. And so if performance is not a problem, you should at least use 128 bits for good security. If you really want strong long-term security, then you go to the double, 256 bits. So this is what we usually do. If performance is a problem, then you should really know what you are doing, or you can hire me, and then I will do some consultancy. No, I'm joking. We also see in the blockchain space that people, like they discussed this, you can see, oh, well, we do not 128 bits, but we are doing 111 bits. So this is something that you sometimes see when we discuss, for instance, elliptic curve security. Next slide, please. Here is just an idea of what are big numbers, what are small numbers. If you look at the end, so it says something like this is. You see the number of 65-digit primes. Actually, 65-digit by now is very small, but I show this to explain to people that there are many primes. The amount of primes, even though their relative frequency is low, their absolute quantity is enormous. So the probability that if you and I that we create a random prime, that we use the same prime is completely negligible. At the bottom, you can also see that we, well, let's take the one at the bottom, the very bottom is like the winning the lottery here in Brazil. And what we usually do is that in cryptography, we define 2 to the minus 80. And I ask my students to compute, and this is like winning this lottery like 5 times in a row. So you should understand that the security margins in cryptography are really small. Okay, next slide. So I'm going to give you 2 important examples of a cryptographic algorithm. Now, the first one, I'm going to first give an insecure example. So here what you see is, on the second row, you see the message which says this crypto system is not secure. And on the first row, the first line, you see the key, the encryption key. This is simply the word cipher. And the way that we encrypt it is as follows. We write the key next to the message, and if we get to the end of the key, we repeat it as many times as is necessary to encrypt the plain text message. And what we do, the operation we do is like we are adding letters. So the addition is like A plus A equals A plus A plus B equals B, and that's the way the operation that we are doing. If you represent each letter by a number, then this would be like addition modulo 26. But it's like letters, you are adding letters. And by the way, if you get to the end of the alphabet, if you get beyond Z, then you go back to the letters A, B, C. So this is the addition. This is the operation. So in this addition, if we look at the first column, then C plus T will equal V, and I plus H will equal P. etc., etc. So this is the Vigenère cipher. So please scroll down and we will see some additional text. So as I said, the addition operation is modulo 26 and it can be summarized in a table or using a slide rule or a disk. So this is called the Vigenère table. You can even find it on Google, Wikipedia, I'm sorry. This cipher is very, very old. It's from 1553, and it was completely broken in 1863. So it's somewhat surprising that, like 20 years ago, a company called WordPerfect, they used it in their way to encode the documents. And it was like so amateuristic because it could be broken very easily. So what you must understand is that if you know what the key length is, if you look at the column that when there is a C, so you get C as added to T will give you a V, C added to Y will give you A. You can do a statistical analysis on that, and so you can, if you know the size, then you can isolate each column and do statistical analysis for each of these columns. And the other thing is that if you do a statistical analysis and you got the size wrong, you will get a random distribution, whereas if you get the size correct, then you will get a very distinct distribution. So it's not very difficult to break it. I often give it as an exercise for my students. And even the attack is simple. More sophisticated attacks, which gives you an answer very quickly, exist for the Vigenère cipher. But the importance of the Vigenère cipher is the next slide, please. Because it's the same as the Vigenère, except now that the key never repeats. So instead of having on the first line, I do have a word, a key that I repeat, I will have a completely random sequence of letters. And now this is really, really interesting because if I know that the distribution of all these letters in the first line is uniform, so each letter has a probability of 1/26, then I can prove that this system has absolute security, that even with a supercomputer, you won't be able to break the system. So this is called, the system is, therefore I explained it, and the system is very important. It's called the one-time pad. And again, so the secret symbol in the first line, the key symbol in the first line, they all have the same probability. And I'm going to give you a short explanation on the next slide why it's so secure. So look at the first column, that you will see there's the key symbol is the N and the plaintext symbol is the T, and the resulting ciphertext is the H. Now please scroll down. Okay, now the point is that if you look at the second line here, so the adversary sees the ciphertext symbol, which is the H. But now this H can be the result of many key and message pairs. So it can, because this H can be A plus G, or B plus F, or C plus E, or N plus T, or X plus J, Y plus I, Z plus H. And all these 26 possibilities are equally probable. So the adversary who gets to see the H cannot figure out what was the original message symbol that was being sent. And this argument is true in each and every symbol of the message. So this is why the one-time pad is absolutely secure. Next slide, please. Oh yeah, this is just repeating there was an additional line. Yeah, okay. There was a one-time pattern additional world. Yeah, scroll down one more. Yeah, so here is the one-time pattern in digital world. Instead of using letters, we now use bits. The addition is not modulo 26, but it's modulo 2. And what mathematicians call addition modulo 2 in computer science is called the exclusive OR, which is explained, everybody knows. So we have a random key, we have a plain text, and then we do the exclusive OR to get to the ciphertext. So the exclusive OR is one of the most important operations in all cryptography. This is really, exclusive OR is overwhelmingly important in cryptography. And the argument now is the same. Suppose that the adversary sees the ciphertext symbol, a 0, then he cannot decide if it's the message and key is 0, 0 or 1, 1. And each has the same probability, so he can't figure out. Now, next slide, we must talk about the disadvantages of the one-time pad. So this is really important that you must understand. In a one-time pad, the key size must be at least the message size. And actually, this is a big spoiler. Suppose that you have a source of randomness, like, I don't know, you have source of data that's producing 1 gigabit per second, then you would also need to generate 1 gigabit per second of random numbers, of random bits, and you would need to transport that. So that is really a problem. I cite here 2 or 3 famous cases. So Venona was the following: the U.S. government, the Secret Service, they discovered that the Russians, they were recycling key material for the one-time pad, and so they were able to break the system. It's also the case that one must destroy the messages. In the case of Che Guevara, he didn't do that. So when he was caught, they could still figure out, they knew what keys he was using. They had intercepted the message, so they could decrypt the message and still reconstruct what he had been doing. So in practice, the one-time pad, even though it's theoretically perfect, in practice, it's not hardly ever being used. I do think that some governments, for diplomatic material, they may still use the one-time pad. Next slide, please. But it still has very important implications. It's the first scheme in history which had a mathematical proof, and it was Claude Shannon who, during the Second World War, who produced this proof. It has been a source of inspiration for definitions of security, and it's also, if instead of using true random numbers, you can use pseudo-random numbers, then you also get to a good secure scheme. Okay, so this is about the one-time pad. Now we go to skip a little bit, skip many decades of advancements. So I hope that in some other class somebody will explain what the advanced encryption standard is about, but this is the scheme that I've shown earlier. It's like Alice and Bob, they communicate and they use the encryption algorithm, and in this particular case, it's the advanced encryption standard. The advanced encryption standard has fixed length. You can have 128 secret key, 192 secret key, and 200 fixed secret key. The block size usually is at 128 bits, but now you get to a different problem, and it's a problem that I mentioned in the very beginning, is how do Alice and Bob know the secret key K? I said that they could use, I don't know, a courier, or they meet. But what if they cannot meet? So Alice is in Tokyo and Bob is in Singapore, and what can they do to define a key K which they both know, but with anybody else who is spying on them on the channel won't be able to use. So this is what the next slide is about, the Diffie-Hellman key exchange. So this involves some mathematics, okay, and this will be explained in more detail in a later session. But all the arithmetic here is done modulo some prime number. So what you must know about the modulo operation, it's like you do the division, but instead of staying with the quotient, you are throwing away the quotient and you are staying with the remainder. So if you divide, if you take like 16 modulo 11, so 16 modulo 11, the quotient will be 1, but the remainder will be 5, right? 16 minus 11 will give you 5. So 16 modulo 11 equals 5. So this is the kind of operation that we are using, okay? And what happens is now is the following. So Alice chooses a random number, an exponent a, and it's going to compute g to the power a, where g and p are some magic numbers which have some, so p is a prime number and g is a number which has a special property. And then it's going to compute uppercase a, and Bob does exactly the same thing. So Bob is choosing a different random number, lowercase b, an exponent computes b equals g to the power b. And they send these values a and b to each other. And now each of them will take the other's message and raise it to its own random exponent. So this is what you see. So Alice will produce the k of a, which is taking Bob's message and raise it to its own private exponent a. And Bob does exactly the same. And if we scroll down, then we will see that in fact these messages are the same. Because if you look at what happens is that when Alice computes b to the power a, well, this b is g to the exponent b times a, but this is the same as g to the a times b. G to the a is equal to uppercase a. So what we see is that the key that Alice computes and the key that Bob computes, they are exactly the same. So this is a good start. Now the next question that we must address is, please scroll down. What does the adversary see? Well, let me just make an observation before I answer that question. Because the protocol is often called Diffie-Hellman key exchange, but note that there is no exchange of a key. They are defining a key. They are establishing a key. So it would be more appropriate to call this protocol Diffie-Hellman key establishment. This is what the protocol establishes. Next slide, please. So here, the adversary, if the adversary intercepts the channel in the middle, then what the adversary sees is g to the power a and g to the power b, and of course it can compute the product of a and b, but this is g to the a times g to the b, which equals g to the a plus b. But this is not what k is. K is g to the exponent a times b. And now here things get a little bit complicated, but we will assume that an adversary is not able to compute the product AB from this exponent. And there are two, you can please scroll down. One of the underlying definitions here is what's called the discrete logarithm problem, which is defined as follows. So suppose that P is a prime number, and G is what's called the generator. A generator means that it will produce all elements in some arbitrary order. And now suppose that we compute H is equal to G to the power X, where X is some random number. Then we call X the discrete logarithm of H. And if we scroll down, we assume that given, yeah, please go on. Given, so this defines the discrete logarithm, the discrete log problem. If I give you P, G, and H, and I ask you what is the value of X such that G to the power X is equal to H modulo P, you cannot compute that for prime numbers that are 1024 bits or bigger than that. So that's in a sense is the discrete log problem, and this is the basis of the Verifiable key exchange security. Yeah, please scroll down. Yeah, okay, we can skip that. Now, yeah, so we get for three notions of security. So, and this is, I find this very important. So this is why I present it here. You must always keep in mind that in cryptography, there exist three different kinds of security. One of them is called unconditional security. And the example is exactly what we have just seen. It's the one-time pad. It's secure against an infinitely powerful adversary. And forgive me if you are religious, but I always say that even God cannot compute cannot break the system. So the securities, even if you have an infinitely powerful adversary, it cannot be broken. The security are based on mathematics, rigorous mathematics and probability. So this is the first one, unconditional security. The second one on the next slide is computational security. So the example that I gave just about the Verifiable key exchange, this is a good example. It's based on the discrete log assumption. It's a little bit more tricky than that, but I'm going to skip that. The idea is that we assume the existence of problems which we know that for sufficiently large parameters, they cannot be computed efficiently. And I presume most of you already have heard of RSA, the RSA assumption. This is about you compute the product of two prime numbers, and you get the value n, but given n, it's very difficult to recover the original primes p and q. The discrete log problem, as I just said, it's you have these values, you have h equals g to the power x, but it's very hard to recover the value x just given h and g. And so you must recall that proofs in this case are always based on the security reduction. In the following sense, if the adversary can break the protocol, then this implies that he has found an efficient algorithm for problem XYZ. But we know that XYZ is difficult. This is what we believe. And so we assume that the security of this protocol is sound because it's based on some hard problem. So this is the essence of computational security. And there's the next slide will present the practical security. So this is what, if we discuss hash functions, or if we discuss the advanced encryption standard, re-encryption, what we do is that we assume that that the security has a word factor of 128 bits. So this makes it secure against any real-world adversary. And what this has been the tradition is that these algorithms, they are completely, how do I say, they are open source, so everybody can see what the algorithm is about, and they have been peer-reviewed, and so we believe that they are secure. But we have no proof that they are secure. There's no mathematical proof that they are secure. So this is sort of a very very funny situation. I'm not sure if it's on the next slide, but in fact, if we look at security, yeah, so it's there. All practical cryptographic protocols, they are based on some assumptions. We have no proof that they actually are secure. We believe that factoring is hard. We believe that discrete logarithm problem is hard. We believe that AES is secure, but we have no actual mathematical proof of their security. We also, there exist other assumptions, but let's not elaborate on that. But so I have another paper, and it says like, well, cryptography is actually like a house of cards. It's all based on assumptions. If these assumptions break down, then everything breaks down. But the chances are very small that these assumptions do break down. Okay, next slide. Yeah, okay, so we're getting towards the end, which I think is good, looking at the watch. So what we see, what's sort of new, is that crypto is exploding, and that the nature of cryptography is changing. It used to be like 20, 50 years ago, it used to be all about network security, encryption, authentication, digital signatures, SSL, TLS. And what we are seeing, because of the Bitcoin, the blockchain explosion, we see now a focus on integrity, transparency, privacy, shared computation. And the new buzzwords are zero knowledge, homomorphic encryption, and multi-party computation. So I'm gonna, for the last 10 more minutes or so, I'm gonna explain high level what's going on. So one of the problems that we have is what I call outsourcing a computation. So suppose we have a very small client, and he wants to outsource a computation to the cloud, maybe to the Amazon cluster service. Now, of course, we know that this can be done, but please go to the next slide. The question now is, how can the client, I'm sorry. So we have, no, please go on the next slide. Yeah. So this is the same setting, but it's the same scenario, but a different diagram. On the right, we have the user. On the left, we have the cluster. And so the user asked, oh, please compute the f of x for me. And the cluster now answers and says, well, the result is y. But then the question, of course, is about correctness. Why should the verifier trust the result? Why should the verifier have confidence that the cluster isn't fooling him and is just sending a different answer. So this is the main question that we are going to resolve in the next few minutes and in the next class 2 weeks from now. I just want to say that the privacy of the user is not a topic. The privacy of the user in this case is a different topic, and this is what we would have to use fully homomorphic encryption. Okay, now next slide, yes. So as I said, how can the verifier I'm sorry, I'm distracted here. How can the verifier be sure that the result is correct? Now, so one of the things that the proofer could do is it could send a dump of the whole computation to the verifier, but of course this is not very sure. This is terrible. This is a big big computation. So what we want, please, next slide. What we want is that the verifier shows a succinct witness that this is correct. So this is what a snark is all about. It is a succinct proof of showing that the computation is correct. What does succinct mean? It means that it's short. It should be easy to verify. It should be short in size, and the verifier should be able to, even with a weak computational platform, should be able to verify it. So SNARK stands for Succinct Non-Interactive Argument of Knowledge. Given the time, I would like to start the next time I will speak. I will start at this point and I will explain actually what this actually all means and what this is all about. So as far as I'm concerned, I would like to stop. We can go to the last slide.
Yes, and that's perfect, because we're going to have a separate dedicated.
Yeah, I'm sorry, but I'm running out of my time also on my end. So
no, I think we are good, because we are going to have dedicated session on snarks and such. Yeah. So
yeah, well, I'm gonna start with 5 in this session on snarks and explain it all in detail.
Okay.
So I would like to wrap it up here.
Perfect. Thank you so much, Dr. Graaf. It was an honor to have you. This session was very stimulating. I think we went over most of the introductory concepts of cryptography, Diffie-Hellman, discrete log problems, and things like that. So again, we had some hiccups with some denial of service attacks, sort of, but we'll take care of that. Again, thank you everyone for joining. Thank you, Dr. Graaf, for your time.